future. And I referred to one paper from last year where there are 5 authors, and you can see that all of the authors except me have names from China. And so I think that this conference has a very appropriate title because the work I'll talk about involves seminal interactions with China. And I could mention that in the past 5 years that I've been collaborating with many wonderful young people from China, that I've got to know and work with students, postdocs, and others from collaborators from 15 different Chinese institutions. And there's a tremendous resource of talent in that country. And I believe it's not appropriately recognized in the West. So I hope this will change in the future. So I love to put pictures in my talks, and I'll start with some pictures of my Chinese friends. And the one who really got me involved with China is Li Mingge, who was a student of Dick Caddison. And it was jointly at the University of New Hampshire where we had a joint seminar for a number of years, and the Chinese Academy of Sciences. And the 3 people who, in the work I'll talk about, started this work are Qinleng Zhang, who's a professor of mathematics at Hebei Normal University, Chengwei Liu, who from 2015 to 19 was my postdoctoral fellow. He had a PhD with Vaughan Jones in Vanderbilt, and now he went from being postdoctoral fellow immediately to being full professor at Tsinghua University. And Jiang-Liu Wu, who now is at the Beijing Institute for Mathematical Sciences and Applications, and spent over 3 years, a year at Harvard. And you see he has some other seminal interactions in his arm. And I could mention Rencheng Ren, who's my current postdoctoral fellow and helped me a great deal with the illustrations for this talk, because he's very good at drawing pictures in LaTeX. And here are 2 other current postdoctoral fellows, Kaifeng Bu and Zhen Yang. Were sitting in my office at Harvard last week. And there are a number of other Chinese collaborators that I've had over the past couple of years. But also, the work I'll do has some relation to quantum information and quantum computing. And the lead in Shanghai of quantum computing is Pan Jianwei. And here, when I visited his institute in 2018, he's showing the dedication of the institute, which now has a computer with over 250 qubits. And he predicted that in a couple of years, they'll have millions. So let's get started on quantum Fourier analysis. So I'll start with classical Fourier analysis because there's an analogy between the 2. And we know the Fourier transform on the real line. And the adjoint of the Fourier transform is its inverse. And we also have convolution. So the Fourier transform exchanges multiplication with convolution, so that the Fourier transform of a convolution is the product of the Fourier transforms. And this is all abelian, so it doesn't matter what order you write things. So another way you could define the convolution is the inverse Fourier transform of the product of Fourier transforms. So the Fourier transform is unitary on L2. That's the famous Fourier inversion theorem or Plancherel formula. The absolute integral square of the absolute value of the Fourier transform integrated is the square of the integral of f. But the Fourier transform also maps integral functions to bounded functions, and that's a very elementary inequality. You just put the absolute value into the definition of the Fourier transform so that the L infinity norm of f is bounded by the L1 norm. The L infinity norm of the Fourier transform. And therefore, the Ries-Thoren interpolation theorem says for dual indices P and Q, where 1 over P plus 1 over Q is 1 and Q is greater than 2, that you can interpolate the norm of the transform going from LP to LQ as an interpolation of the norms on the two spaces. And the norm on each of these spaces for the Fourier transform is 1, as we just saw. So this gives norm 1 from LP to LQ. And this is known as the Hausdorff-Young inequality. And there's also the classical entropy of f, which is minus the integral of absolute f squared times log f squared. Sometimes it's defined a little differently, but I'm going to use this definition. And there's a relation between the Hausdorff-Young inequality and the entropy, which is that the derivative of the P norm of f is given by this formula, which involves the entropy when P equals 2. And so if we set P equals 2 and the norm of f in the L2 space equal 1, we have the derivative of f is equal to minus a quarter of the entropy of f, the derivative of the LP norm of f. And this is leading to the Hirschman uncertainty principle, which was discovered by Hirschman in 1957, which is that the entropy of f and the entropy of the Fourier transform of f add up to a positive number. And how do you establish this result, which was proved by Hirschman? You look at the Hausdorff-Young inequality, which says that the P norm of f minus the Q norm of the Fourier transform is positive for Q greater than 2. And if you kick Q equals P equals 2, then K vanishes because f is unitary. So if you draw the function K of Q for Q greater than 2 against Q, it's positive and vanishes 2. So the derivative is positive at 2. And to compute that derivative, you just use the previous formula and the fact that P and Q are changing in opposite direction at 2. And that gives the Hirschman inequality. Now, Hirschman conjectured in 1957 that the constant was on the right-hand side was not 0, but there's a strictly positive constant for which the entropy of f plus the entropy of the Fourier transform of f is greater than that constant. And he conjectured the constant came from testing the Gaussian. And this is proved by Beckner in 1975. So the Beckner uncertainty principle increases the constant to log E over 2. And where does this come from? It comes from the improved inequality proved by Beckner, better than the Hausdorff-Young inequality for Q greater than 2. where the norm is given by P to the 1 over 2P, Q over Q to the 1 over 2Q, which is a constant strictly less than 1 in between. So if you take the derivative of that function with respect to Q, the coefficient, you get minus a quarter log E over 2. And that provides the correction to the Hirschman uncertainty principle and yields the Beckner uncertainty principle. So Beckner also proved that the Gaussians minimize this Beckner inequality. And this was shown by Bieleniczky-Berula and collaborator that you can, from this inequality, derive the Heisenberg uncertainty principle for P and Q. And Elliott Lieb in 1990, so 15 years later, showed that only Gaussians give equality, or translations of Gaussians. And there's much other related work afterwards on this inequality. So now let me come to quantum Fourier analysis. This began in the work I'm talking about, 2016 in planar algebras, but it's touched base with many other mathematical frameworks: fusion algebras, fusion categories, locally compact quantum groups, and surface algebras. And presumably is connected to many others. So what is a planar algebra? This was invented by Vaughan Jones. And it's a pictorial representation in the plane of transformations. And I'll, in this talk, specialize to 2 ins and 2 outs given by those lines at the top and bottom. And a transformation T is represented by this diagram. In planar algebra, it's called the 2-box. And the adjoint is given by a vertical reflection. So the idea here is that you have an algebra of pictures, and this forms a picture language for mathematics. And there are theorems that you can prove about the pictures. The trace is defined by connecting the lines at top and bottom without crossing. And this corresponds in matrix algebra to an unnormalized trace. The trace of the identity of a D by D matrix is D. These diagrams in planar algebras are invariant under isotopy, but you're not allowed to move lines across each other. And there's an additional property we need, which is called the spherical property. That is, you can think of the plane being compactified to a sphere. And therefore, on the sphere, you could take this trace, which is defined on the right-hand side, around the back to be on the left-hand side. A product of transformation is given from top. It acts on the top, so the product goes from bottom to top. It's vertical in the usual notation in planar algebras. So T times S is the S box over the T box. And the trace then is cyclic, which you can immediately see by drawing the picture with the product formula and doing an isotopy, moving S on the top to S on the bottom. But in order to have a Hilbert space realization, you need more than cyclicity of the trace, you need positivity. And then you can use GNS representation from the pictures to get a Hilbert space. And you define the putative inner product as the trace of T star S. So T star S is inverted T times S. And what you need to get a Hilbert space is, if you have S equals T, it has to be greater than or equal to 0. That's positivity of the trace. That if you take trace of a positive transformation, you get a positive number. So the famous classic theorem of von Jones is the index theorem, that there's certain values of the circle that allow positivity. And this is proved in terms of the temporally Lieb algebra with an arbitrary number of elements. And Jones' theorem is that the circle, which is always denoted by small delta, is either quantized with values 2 times cosine pi over k for k equals 3, 4, 5, and so on, or in the continuum 2 to infinity. So this is where quantum comes in, because the delta, which is the quantum dimension or the square root of quantum dimension, the square is the Jones index, has this quantized behavior. And the temporally Lieb algebra, here I've drawn the, if you have n strings, and the third one is the start of this up cap and cap. The generators ease of the temporally Lieb algebra of these diagrams. So where does Fourier analysis come in? The picture Fourier transform is obtained by permuting the lines, taking the top right input line, making it output, and the bottom left output line to making it input. As operation of this sort was introduced by Agnaiano in his study of paragroups in the 1980s. But this turns out to be really important input to the subject of quantum Fourier analysis. So here's the way the Fourier transform of a picture is defined. So the Fourier transform is unitary on L2. L2 is defined by the inner product that I mentioned. And if we draw the Fourier transform of T times its adjoint and multiply them, you see the picture here. And now to get to L2, you would take the trace of the left side equals the trace of the right side. So you use isotopy and the spherical property, and then the two sides, the trace are equal. So the Fourier transform is unitary on L2. And that means the Fourier transform of T has the same inner product with itself as T. Now, there are two different multiplications actually for the pictures I've drawn. There's the normal product that I've described up to now, and the convolution product, which is obtained by, instead of this vertical multiplication, some type of horizontal multiplication. And the Fourier transform, like in the classical case, intertwines these two products. Because if we write the Fourier transform of T, times the Fourier transform of S, and use an isotopic to put things on the same line, this is just the Fourier transform of T star S. So we could define the convolution, if we wanted, as the inverse Fourier transform of the Fourier transforms of the products. Now, in order to get analysis, we need some norms, and I'm going to talk about the Schotten norms, which are the most elementary LP norms. You take the absolute value of the self-joint T star T to the power P over 2, take its trace to the power 1 over P. And we've just seen that F is unitary on L2. So what can you say about L1 to L infinity? We saw in the classical case, the norm was 1. So I'd first start with a simple example. Let's take this P, which is 1 over the circle times the cap cup. So this P is a projection, because if we multiply it itself, we get a circle which will cancel one of the factors, 1 over delta. And it's clearly also self-adjoint because it's equal to its vertical reflection. And what is the Fourier transform? Well, after isotoping, it's just 1 over delta times 2 straight lines, which is the identity. So the Fourier transform of P is a multiple of a projection. It's the identity times a constant. The identity is a projection. And something with the property that it's a projection and its Fourier transform is a projection times a constant is called a biprojection. And by simple calculation, we see that the operator norm of, or the infinity norm of the Fourier transform of P, which is looking at the upper right picture, just 1 over delta times the norm of 1, which is 1. So it's 1 over delta. Well, the trace norm of P, the L1 norm, got by joining the top and bottom lines, as we did before, gives the circle, which just cancels delta, so it's 1. So we have the identity that the infinity norm of the Fourier transform of P is equal to 1 over delta times the L1 norm of P. So this is different from the classical inequality where the constant was 1. So there's a quantum inequality, which is just this one, that the operator norm of the Fourier transform of T is less than 1 over delta times the L1 norm of T. And this was proved by Jiang-Liu and Wu, first 3 pictures, paper in Journal of Functional Analysis, 2016. So by the Ries-Thoren interpolation theorem, we get an inequality from LP to LQ, which is just like the classical theorem. One of the norms is 2, 2. One of them is 1 infinity. And therefore, delta turns out to be raised to the power minus 1 minus 2 over Q. Q is greater than or equal to 2. And they also showed that biprojections and the generalization of translations of biprojections give equality. So they found the minimizers. And so the constant is optimal. So the biprojections in quantum Fourier analysis play the role of the Gaussians in classical Fourier analysis. And this leads to an uncertainty principle where the phenomenon entropy replaces the classical entropy. So the phenomenon entropy is just the trace of the absolute value of t squared log t squared. And we're going to assume that the L2 norm of t is 1, as it's the formulas we gave in the classical case. And the uncertainty principle that comes from this Jiang-Liu-Wu inequality is that the phenomenon entropy of t plus the phenomenon entropy of the Fourier transform is greater than 2 log delta, where delta is the value of the circle. And it's given by the index theorem as quantized value if it's less than 2 or in the continuum from 2 to infinity, and its smallest value is 1. So this comes from the fact that the derivative of that norm is, in the quantum case, minus 1/2 log delta. And that replaces the classical equality, minus 1/4 log e over 2. And so that leads to the constant 2 log delta and the uncertainty principle. Now, I thought I'd give you an idea of how to prove this. It's totally in terms of pictures. So maybe I go through this part of the talk quickly and come back, but I want to show you, you can give a proof of this inequality in terms of pictures. This is basically the proof in that paper I quoted, but simplified somewhat. So there are 2 steps. First is to prove it's true if T is a rank 1 partial isometry. And second, reduce the general case to that case. So really the pictures come into the first step. And the pictures make very clear what's going on. Well, if you just look at the analysis, it looks complicated. And the first sub-step in proving step 1 is to show that this diagram is a self-adjoint projection. And this is for an irreducible subfactor planar algebra. So to show that, you multiply this transformation by its adjoint. And since this V is assumed to be a partial isometry, V star V is a projection, but the absolute value of a projection is itself. So in the middle, the 2 products, the product in the middle just is the absolute value of V with a partial trace on the left. And I claim that you can show that that box surrounded by the dotted line is just the coefficient, the L1 norm of V divided by delta. So in an irreducible planar algebra, if you have a transformation with 1 line on the top and 1 line on the bottom, it's just a constant times the single line. And you can evaluate this constant then by taking the trace. So if we take the trace on the left, we get the trace of the absolute value of V. If we take the trace on the right, we get delta, which cancels the delta in the denominator. And so this diagram is just a multiple of the original one. So the next step, using this, is to show that this transformation is less than, this is a single line times the absolute value of V. Now, the way to see this is to look at the inequality we proved and use that method again to evaluate the thing on the right. Now, why is the first inequality true? Because both of the elements on the left inequality are projections. And it's easy to multiply the two and see that the one on the left is a subprojection of the one on the right. So it's less than or equal. And using this method, we can evaluate the constant. And now to complete the proof, all you have to do is to multiply by the constant on the left, inverse. And the diagram in the blue on the right, the first element is just the Fourier transform of V adjoint times the Fourier transform of V. So we've shown that it's less than the L1 norm of V over delta squared. So that's the simple case. By taking the operator norm and using the C-star property, we have the desired inequality for partial isometry of rank 1. And then the reduction is just an algebraic thing. I won't give the details. So let's go back now to classical Fourier analysis. There are also many results for the Fourier transform from LP to LQ for non-dual indices in the case that 1 over P plus 1 over Q is not equal to 1. For instance, for finite groups. And if you take a finite abelian group G of cardinality absolute G, then Hilbert and Rozotnik in 2010 showed the norm of the Fourier transform is a certain constant C, depending upon P and Q, but now P and Q are arbitrary. And to go to an infinite case, infinite group case, you need to have dual indices, 1 over P plus 1 over Q equals 1. But for the finite case, this is true for all. And Liu and Wu in 2019, and now published last year in Science China Mathematics, proved that you get the same bound for planar algebras where the cardinality of G is replaced by delta squared, the Jones index. And Madman and Peng Xu have some results on locally compact groups in 2020. And here's a picture of what the constant is for the planar algebras. So the plot is for the index P and Q, plotted 1 over P versus 1 over Q vertically. And the red line at the bottom is the dual case. But there are 3 regions where the norm of the Fourier transform is given by the red formulas, the delta to a certain power, depending upon Q and P and the 3 regions. And on the borders, you can see that the formulas agree. And in that case, the Gilbert-Rezotnik regions are just the same, and the bound is the same, except that G, the cardinality of the finite abelian group, corresponds to the square of delta. And they also determine the extremizers. And they're labeled here in this diagram. So for the self-dual case, they're by projections on the red line. But there are other types of minimizers in the other cases, and they're all understood. Now, there's a variation of planar algebras, which we call planar power algebra of order D, where on the line, you introduce a label, which is an element of the cyclic group ZD. So we think of this in mathematical physics as a charge, and the charges are additive in the group ZD. So the charge D corresponds to no charge, which is the identity. And now in this planar para algebra, there's no longer invariance under isotopy, but if you move things vertically past one another, there's a phase depending upon the charges moved past each other. Q is a root of unity, a dth root of unity, and it's raised to the power KL. So it's useful to have an interpolated product where you don't move the charges past each other, but put them at the same level. And then the constant that interpolates is the square root of Q. And this is something in the pictures that's a little harder to explain algebraically. But it's very natural from this point of view. And the square root of Q that you choose, you have 2 choices with plus or minus sign, has to be one where Q to the D squared is 1. Zeta to the D squared is 1. Q to the D squared is always 1. So D equals 2 is the fermionic case. D equals 3 and higher in quantum information is called qubits. So there's a modified index theorem, which is the same result, but you have to take the ratio of the circle over the square root of the order D. So the minimum value of delta is square root of D. So the usual case for qubits in quantum information is k equals 3 and delta square root of D. So I claim that in this framework, the quantum Fourier transform generalizes the classical Fourier transform. And if we take the classical Fourier transform of this labeled cup cap, which is just given by the usual formula Q to the KL, which is this factor coming into the para-isotopy, then the quantum and classical Fourier transforms are equal. I'm not going to go into the proof, but it's possible to see that that's true. So in the sense that on this neutral subspace, the quantum Fourier transform generalizes the classical Fourier transform. So their relation to quantum information that I've alluded to, the pictures for the Pauli XYZ operators. And here is the answer. They're both single charge diagrams. Oh, no, Z has total charge 0, sorry. X and Y are charge plus or minus 1. And this is an algebra that satisfies X, Y, or Z to the dth power is 1. X, Y is Q, Y, X, and cyclic permutations of that relation for X, Y, and Z. And X times Y times Z is the square root of Q, satisfying zeta to the d squared is 1. So for d equals 2, these are just the usual SU2 infinitesimal generators, but the Pauli matrices, but for arbitrary d, these pictures work. So you can use these pictures then in quantum information to describe and find protocols and algorithms, and there are many papers about this since 2016. So this is two-dimensional language we call the charge string language for quantum information. Of course, pictures in quantum information are not new. Bramsky and Koka studied category theory in quantum information, and pictures in mathematical physics go back to Feynman, maybe before. There's also a three-dimensional language we call QAnon, which was discovered in 2017. And there, the qubit states, instead of being represented by charge states, are represented by neutral pairs. So it's like in superconductivity where you have pairs. And the single qubit states are pairs with each with charge plus or minus 1. So they're made up of transformations will have 4 endpoints on single qubits from doubling the charge string picture, where there, 4 inputs, 4 outputs. So this leads to a picture of a topological field theory in 3 dimensions with the strings given as defects in the topological field theory. I had to mention quantum field theory. So here's a picture of a 1 QAnon operation, which is the analog of the planar algebra T, going from top input to bottom output with the strings going into the state. So the identity transformation is just 4 straight red lines. The Pauli Z is charge 1 on one line, charge -1 on another. There are different ways you can label them, but this is a standard one. And the Hadamard matrix, which is the Fourier transform, is given by the classical Fourier transform, which is given by this picture. So if you have a 3-qubit to 3-qubit transformation, you have a diagram looking like topological field theory with these defect lines. And the point of having the ends, these 4 string ends, is to ensure that you come into a 1-qubit state, which is neutral. So there's an amazing identity or relation. If you have a genus in your topological field theory, and you have a string, the red line in the middle, going around the genus, you can remove the genus and that red string and replace them by a constant 1/√d. And this leads to many interesting relations in this picture algebra QAnon. So there are more recent results that I'm not going to talk about. Liu, Sebastian Palco, and Wu proved in a series of papers, the first 2, I think, are now on the archive, the last one's still being written, that you could use this quantum Fourier analysis and the sure positivity theorem, which for pictures A and B, which are positive transformations, leads to the convolution of AB being positive, which is easy to prove in pictures. That certain fusion rings cannot be categorized. And this was an open problem in algebra for a long time, and solved by this quantum Fourier analysis. And there are actually fusion rings of rank 7 that they studied, and now they're studying many others. So Vigberson, his son, wrote a paper recently on general uncertainty for Hadamard matrices. And this relates to this quantum Fourier analysis. It's just been published this year in the Bulletin of the American Mathematical Society. Vigberson is a computer scientist at the Institute for Advanced Study in Princeton. And there's a recent preprint on the archive about uncertainty principles in Neumann algebras. So 2 questions for the future. There are many interesting open analytic questions. For instance, there's a pictorial generalization of the central limit theorem, which is conjectured, but it's not proved. There are many, many open questions in that paper I mentioned at the start of the talk. I think there are 20 at the end of the paper. This is one of them. But more importantly, to what extent this should be QFA, should quantum Fourier analysis be as important as classical Fourier analysis? Classical Fourier analysis comes into everything. It was invented to study the heat equation or migration of fish, but ultimately turned out to be important in practically every field of mathematics and physics and engineering and economy and everything. And to what extent will quantum Fourier analysis be important? So I'm very excited about this question, and I'm really looking forward to seeing many different answers to this question. And so I want to say thank you. And a little postscript, since there's so close a connection with China, when I traveled to China last time in 2019, I learned how to say thank you there too. Yes, yes. It's subfactor planar algebras with these markings. And there's a generalization of these abelian markings. So for non-abelian ones, anions. Well, that's this latest paper that I mentioned goes in that direction.
The biprojections that you mentioned are closely related to intermediate subfactors in the, as has been understood, I think, by Jones and Fish. Can be seen clearly in Roberto's Q system approach. What's the interpretation? Is there a connection? Is there an interpretation of this fact in your inequalities?
Biprojections play the role of Gaussians is really fascinating, but exactly what the relation is, it's still to be discovered. And I'd certainly like to know the connection with the work of Bish and Jones. So, yes. Maybe somebody here can comment on that. You have to tell me what the question is because I don't see the online. Can somebody read the question?
And you can ask yourself.
Oh, yeah. Do you hear me?
Yes.
Yeah. Okay. Arthur, wonderful talk.
Thank you. Who is this?
Henning Rehren.
Ah, hi.
Yes, I should.
I can't see you, but it's good to hear your voice.
Yeah. Thank you for this talk. I have a question concerning functional calculus. Of course, to define these P norms, you need some functional calculus in the GNS representation of that trace state.
Yes.
But on the other hand, this calculus is somewhat alien to the graphical algebra that you are using, this graphical language. Is there a way to define, say, the square root of an operator or something in this graphical language? It's otherwise so powerful, but I don't see how to use it for powers.
I welcome you to the coterie of people studying quantum Fourier analysis. Maybe you can answer this question.
planar algebras, you have a trace, right? And my question would be if you can think of applications to quantum information or to something else where you do not have the trace condition on either side. So on, well, either on the source planar algebra or on the target. So without trace. So are there applications? That's my first question.
I also don't know the answer to your question.
Good, okay. And
But we are now actually looking at some other algebras that have dissipation built in, the Moitrin algebra. This was also studied by Jones, and it seems to be very interesting, but how to relate it to quantum information is something we're working on.
okay. And also a second question, if I can. For QANs, so the QANs are three-dimensional pictures, right?
Yes.
And you have like a Fourier transformation also in 3D and well, pictorially or not?
Well, in many cases, it's just a rotation by 90 degrees, like in, yeah.
Okay. Okay. Thank you for your talk.
I want to ask, but your formula in the subfactor case is if you translate your work in the subfactor case, do you treat only that two subfactors or general subfactors?
So there's so many different works. When you say my work, this is not all my work, because some of it is my work, but other work is done by many other people that I've quoted. So I don't know.
Any other question? Maybe I can mention that there are papers on infinite index, for example, by Simone Del Vecchio. They might offer a generalization. What?
Yes, the infinite index case is, of course, very interesting, and the, in this QFA group also being worked on. But the problem really is there's so many results and so little time to write them up. And the subject needs other people working on it. And so I really hope that by listening to this lecture, you find it interesting and that other people will work on this subject.
Is there any other question? There is no question online. Okay, if not, we thank again Arthur for this beautiful talk, and there is a coffee break.